Today we're going to discuss the experiment, the oxidation of Borneol. Now, the interesting thing about this experiment is that we're going to be discussing some aspects of green chemistry. And recently, with the move to Strong Hall, we upgraded our labs, and part of the requirements of moving into the new facilities is that we begin to shift our curriculum towards incorporating more aspects of green chemistry. So we're going to spend a little bit of time discussing what exactly we mean by green chemistry and how it kind of impacts our education here at the University of Tennessee. So on this slide, I know there's a lot of text here, and if you want to pause and just take a quick minute to scan through it, that's fine. But as I mentioned, green chemistry is kind of one of the burgeoning fields, we should say, within the realm of not only teaching chemistry, but also with the production and industrial and research scales of chemistry. Now, I think the word green has been thrown around a lot, quite a bit, in a lot of different aspects of everyday life. And so when we're talking about the word green, depending on what field you're in, you're going to have a different definition of it. And even within the realm of chemistry, if we use the term green, depending on if you're talking to an environmental chemist or whether you're talking to an organic chemist, they might have a different interpretation of that. So understand that when I am discussing this stuff on this slide here, this is the definition of green chemistry as expressed by the American Chemical Society. So the American Chemical Society is a governing body within the United States that kind of helps, let's say, guide the larger field of chemistry within the United States. They also produce a lot of scientific journals and publish them, and they develop curriculum, they develop standardized exams. So they're basically kind of just a overall entity that kind of help chemists. So the definition of green chemistry that we'll be discussing, at least, comes from the American Chemical Society. Now, with respect to the term green, as you can see up in the top left-hand side here, right, there's a couple of generic explanations of what we mean by green chemistry. So, in general, we talk about examining the environmental impacts of chemistry. And not only does that mean, hey, we're going to create a new technology to help mitigate carbon dioxide emissions, it could also mean, well, as we're developing this new compound to mitigate carbon dioxide emissions, how is the synthesis and the production of that compound going to affect the environment? And I think this is something that we can kind of relate back to what's going on in the lab. So in the lab, right, you know, we have the very strict policy about not putting anything down the sink. I think that might be the best way that we can express how we immediately impact our environment within the organic teaching labs. When you dispose of your waste in the lab, right? We collect it in these white drums with the filters on them, and at that point, it gets sent off to be reprocessed. And if you recall, in lab we have three different bottles. We have the aqueous, we have the organic, and we have the halogenated. And the reason for that is because the aqueous is processed differently than the halogenated and the non-halogenated. And so I'm just trying to relate this back to the idea of green chemistry, in that, you know, it might seem sometimes onerous that, you know, the specific rules and regulations that we have, but it is for a broader purpose. The second part that we're just talking about here is development of environmentally friendly procedures, and that's going to relate to what we're doing in this particular experiment. Now, the body of this slide here has 12 principles of green chemistry, and those are the principles developed by the American Chemical Society. Now, what we need to pay attention to is that a lot of the experiments that we are doing in this new curriculum and from our textbook here kind of have these 12 principles buried behind the scenes. But specifically, what we're going to be looking at for this experiment, the oxidation of Borneol, we're going to be kind of using a lot of the different, I should say several of the different principles here. So let's just talk real briefly about those. If we look at number 4, right, so we're talking about designing safer chemicals. So camphor, which is what we're going to be trying to produce at the end of this, is something that is, or I should say not something, it is a compound that is actually used quite a bit. You guys might have even seen it before in some of the ingredients lists if you have read it. So camphor is a natural product, right? And it's been used in a lot of medicinal applications. It's got antimicrobial properties. It's an anesthetic. It's a cough suppressant. It's used in the production of as a plasticizer. It's in embalming fluids and pyrotechnics, insect repellents, preservatives, cosmetics. It basically has a lot of different applications to it. And so we're making a product today that's relatively safe. Right? Now, obviously, you don't want to be eating this or rubbing it on your skin, as with anything, right? The dose makes the poison, but camphor is a relatively benign natural product. So we're trying to follow the safer chemical principle here. Number 9 is the discussion of catalysts. Remember, when we're using a catalyst, right, we tend to say that the definition of a catalyst is something that speeds up a chemical reaction, and that's a fair definition. But one of the behind the scenes definition of a catalyst is that it is reused, right? So it is not consumed as this reaction proceeds. And the sodium chloride that we're using in today's lab, right, so specifically the chloride ion, is going to be catalytic in our reaction. And when we go through and look at the proposed mechanism, we'll point that out. So we are using a catalyst for this particular experiment, sodium chloride, and sodium chloride itself is back to point number 4 there, a environmentally and biologically safer chemical. Another point that we're going to be using is the actual solvent itself, right? We're going to be using some different solvents than what are typically used. Ethyl acetate is what we'll be using in here, but typically this, or a similar reaction, we should say, used to be run with diethyl ether. Diethyl ether, while it is biologically safe, it used to be used as an anesthetic. To basically put you to sleep before surgery in a couple of instances. But ethyl acetate tends to be less corrosive than some of the other solvents that we use. Diethyl ether had a big problem that it creates a lot of vapors, and so we do have to pay attention to what happens to those vapors. So ethyl acetate just happens to have some better solvent properties that we're looking for with respect to green chemistry also. And so not every one of these principles is used in every single experiment, but as we go through the semester and as we start to develop new experiments for you guys, we are going to be looking at how we can apply these principles to make the labs here at the University of Tennessee more green, more environmentally friendly, more biologically friendly, and more contemporary with respect to the current trend within chemistry and the broader community. All right, so let's talk about the oxidation of alcohols. So within the textbook, there's several chapters and sections which discuss the oxidation of alcohols. And we could sit here and we could list out quite a few different setups and reagents that we can use for this, right? We have things like PDC, pyridinium dichromate, and PCC, pyridinium chlorochromate. We have our Swern oxidation, right? That's the one with our DMSO and oxalyl chloride. We have our permanganates, the KMNO4. So there's a lot of different things that we can pick for oxidation. Reduction, right? There's a fair amount of different things that we can use for reduction too. The first reaction that we probably learned in all of organic chemistry was the hydrogenation, right? That's when we have hydrogen over a catalyst such as nickel or palladium or platinum. That is a reduction. So we have hydrogen-based reduction. As we go through into the second semester, we begin to learn about LAH, that's lithium aluminum hydride, or sodium borohydride, NaBH4, and those tend to be very common reducing agents that we use. And so in general, when we say oxidation of alcohols, we have to be specific to what we're trying to accomplish. And so if we take a look at the second bullet point there, right, if we begin as an alcohol, depending on the oxidant that we choose, we can stop at an aldehyde. And then if we pick a different oxidant, we can oxidize all the way to a carboxylic acid. And so different setups and different procedures, right, is what we can use to kind of control how far we want to take this oxidation. Do we want to stop it after a single oxidation, right, at an aldehyde, or do we want to take it all the way to a carboxylic acid? Now remember, right, if we have let's say we have a primary alcohol like ethanol, right, if we choose some kind of oxidant, which we can abbreviate just in brackets with an O, if we choose one kind of oxidant, we can stop it at an aldehyde. And if we pick a different, right, or if we continue with our oxidation or choose a different oxidant, we can take this all the way to a carboxylic acid. But remember, this is only with a primary alcohol. If we have a secondary alcohol, right, it's relatively more tolerant of oxidation, right? Because you can't convert a secondary alcohol into a carboxylic acid, right? You'd have to have some specific conditions. So in general, if we have a secondary alcohol, it's going to stop at a ketone, and that's kind of it. So what we have to pay attention to is if we're dealing with primary alcohols, or if we're dealing with even secondary alcohols, we have to look at tolerance, okay? Or we should say reaction tolerance. And so what I mean with that is depending on the oxidant that we use, not only will we oxidize the alcohol, but there's other functional groups that respond to our oxidants. So things like alkenes and alkynes, amines, right? All these things can get oxidized also. We tend to give very just simple examples when we're going through and studying this in class. But with reaction tolerance, or we should say reactant tolerance also, we have to pay attention as to what else is present and what other functional groups are present within our molecule. Now, if we kind of take this idea of tolerance into the reaction that we're doing in lab with camphor there and Borneol, let's take a look at what the structure of this is. So I'm going to try and draw this as best as we can. It is a bicyclic compound, so it makes it a little bit tricky sometimes. So we have a cyclohexane ring, right? We have a general structure like this, a bridged bicyclic system. We've got some methyl groups that are up here on the top of that bridge head carbon. Excuse me, the bridge carbon. Off of one of the bridge heads, we have another methyl group. And then we have our alcohol over here, okay? So we are looking at, this is Borneol here, okay? And so we have a secondary alcohol. And if we notice, right, we were somewhat clever. I didn't come up with this experiment, but whoever did originally come up with this experiment, there aren't any other functional groups that are really present within this molecule, right? So we don't have to be too careful with how we use our oxidant. Now, what we're going to be using as our oxidant, right? So if we just have our generic setup for an oxidant, we're going to be using something called oxone. Okay, not to be confused with ozone. Oxone is a trade name for the people in the corporation that first developed this. If I get oxone in a bottle, right, it is actually a mix of 3 different salts. But when we start to put this in solution and we add some sodium chloride to it and begin to kind of warm it up and let it get going, what's going to happen is the active part, or what we really care about, or what's going to start doing the work for us, is this potassium peroxomonosulfate. So potassium peroxomonosulfate, the KHSO, excuse me, I miswrote that, KHSO5. I'm so used to sulfate SO4, but excuse me, this is SO5. So we've got an extra oxygen in there. And so if we try and take a look, right, at the Lewis structure for this molecule, right, what we see is that we have a peroxo species. Okay, so sulfur in the middle. We have a couple of double bonds here. So it looks very similar to sulfate, except we've got the double bond. Excuse me, we've got an oxygen bound to another oxygen over here. Okay. So let's just fill in some, some charges and lone pairs. Okay, right. So that is what we're gonna kind of be generating as we go through, and this is what's going to be involved with our catalytic process. Okay, so this potassium peroxo monosulfate. Now, I just want to make a quick point to you that this right here, right? Let me highlight that in a different color. So this peroxo, whenever you see an oxygen bound to another oxygen like that, these are typically going to be functional groups. These peroxos are going to be functional groups that we use for oxidation. And you guys might be familiar with this. MCPBA, right? That's a very common oxidant that we learn about. Hydrogen peroxide, something very common also. Benzoyl peroxides, right? So we have peroxides that are used quite a bit in oxidants. So anytime, right, we see that an oxygen singly bound to another oxygen like that, it's probably a good clue that whatever we're doing is going to cause an oxidation to happen. Okay, so we are going to use this oxone to oxidize our borneol here. And what's going to happen, so let's draw this again, right? We're going to take this and convert it into a ketone. So we're taking our, just clear this up a little bit here, sorry. So we're going to take our alcohol and turn it into a ketone. Now we should pause here for just a second, right? This is our generic or our simplified reaction, I should say, right? And so we are going to come back and we're going to be proving that we actually did this oxidation, right? So for your conclusions, right, for your post-lab report, you're going to be saying, hey, I did this oxidation, right? Prove it to me is what I'm going to say. And so we're going to, again, take NMR and we're going to be taking IR. And so remember, with IR, we're going to be looking at functional groups. So you're going to be looking for the growth of a ketone, right? A carbonyl peak in my IR. And we're going to be looking for the disappearance of an alcohol group, right? So these are going to be our key kind of functional groups that we're going to see change as we go through our IR. Now, what's going to happen with NMR? Well, if we take a quick look here, right? We have this hydrogen here that, right, and we have our hydrogen on our alcohol. So if we take an NMR of our starting material, we should expect to see those hydrogens there. And in our final product, those hydrogens are gone. So we should expect to see not only less peaks, but we should also expect to see our hydrogen bound to our alcohol and that hydrogen bound to our carbon there disappear, okay? And so if we pause and just think a quick second here, if this hydrogen, let's mark it in green, right? Let's think about NMR for just a second. That hydrogen in green is bound to a carbon that's bound to an electron withdrawing group, right? So we expect that peak from that hydrogen to be downfield, right? So we should expect to see a more downfield hydrogen peak disappear. And so hopefully as you go through and you do your reaction, you're going to see a downfield hydrogen peak disappear and you're going to see your IR change. So on the next slide, we'll pick up and we'll talk about the mechanism of how this oxidation is going to work. So let's take a look at the proposed mechanism for the oxidation using oxone. So remember, oxone is just a trade name, right? It's just the name that the company picked for those mixture of salts. And when you put those mixtures of salts in solution, essentially what you're going to end up forming is our potassium peroxo monosulfate, the KHSO5. Now, once we have the KHSO5 in solution, you're going to add some sodium chloride into that. And the chlorine, I should say the chloride, excuse me, the chloride is what's going to start to initiate and kind of be the enabler of the oxidation. So when chloride and the potassium peroxo monosulfate interact, we end up forming this compound here, HOCl, which we would call our hypochlorous acid. So hypochlorous acid. So our hypochlorous acid has been used in the past for some other oxidations. And so it is not unusual to see this for an oxidizing agent. But remember, we're just getting that acid from our oxone. So once we have our hypochlorous acid in solution, what can happen is that it can begin to interact with another acid, okay? So we're going to protonate an acid, which might sound a little bit unusual, but understand that hypochlorous acid is a weak acid, and so it can accept a proton there also, right? And so what happens is we basically end up forming this species here. Okay, so a protonated, oops, let me just clean that up a little bit, a protonated hypochlorous acid. And that's what's going to kind of get this stuff going. Now, our first step here after we've generated that protonated acid is a little bit unusual and might not be exactly what we expect. Now, I'm going to draw our Borneol. I'm going to leave off the methyl groups just to make it a little bit simpler to draw. You can see I'm kind of struggling here. It's kind of challenging to draw these fused ring systems, but that's okay, we got it. Right, so here is our alcohol, and I'm going to leave off the methyl groups just to make it a little bit simpler for me to draw. Now, our Borneol is going to interact with our acid that we just made, but it might not react in the way that you expect. Our alcohol here is going to send a lone pair and hit our chlorine, right? So it's going to attack our chlorine, and we make a bond, and we break a bond. Okay, so we are going to add our chlorine to our alcohol. So let me draw this in red. There's our bond to our chlorine. We've got a hydrogen. So we end up protonating, end up adding a chlorine to our alcohol. And so we end up generating our alcohol there with a positive charge. Now something is going to come along and deprotonate that alcohol. Okay, it could be water, it could be our solvent, it's something. It could be our conjugate base, right? Something is going to come along and deprotonate that alcohol. So I'm just going to generally abbreviate that as a B, right, with a lone pair and a minus charge, right? So some kind of base, water, solvent, something in solution. Okay. So it's going to come in, pluck that off, and kind of help settle that positive charge, right? So after we do that, right, here's what we're left with. Okay. And so now we go into a almost SN2-like mechanism. Now remember, with an SN2, we have to have a good leaving group. And our leaving group in this case is going to be our chlorine. And let me just highlight that in red. This guy right here, right? That chlorine right there is going to end up being our leaving group. So what's going to happen is they propose that water is going to come in, grab that hydrogen, make a double bond here, and kick off our chlorine. So let's draw what happens after these steps. Okay, we had our green bond to oxygen there. Through our mechanism, we added our orange one, so we have our double bond. And at the end of the day, we regened our chloride ion. What you'll notice, our chloride ion is kind of how we got started all the way back up here. Right, so we can call this catalytic with respect to the chlorine there, right? The chlorine got things started, and we ended up regenerating it at the end of it. And you can see we took our alcohol here, right? We took our alcohol here, and we converted that into a ketone here, right? So we caused an oxidation to happen. And so this is the proposed mechanism for oxidation of an alcohol using oxone. We're going to be using sublimation to purify our product. And so I need to talk to you guys a little bit about how sublimation works and how specifically to set up our sublimation devices that we have for you guys in the lab. There's a very common mistake that happens where these aren't set up properly, and then we start to introduce water into our reaction, into our purification, and that water can interfere with some of the things that we're trying to do. Okay. So first of all, sublimation is a purification method, and so we're just using that to separate impurities from our product at the end there. How it works is we're basically going to heat our solid up under vacuum. we're going to heat our solid up under vacuum. That's going to cause it to turn from a solid to a gas directly. In the gas phase, we're going to cool it down rapidly, and so it goes from a gas back into a solid. So something going, let's just write this down here, right? Something going from a solid to a gas, right, is called sublimation. And if we go from a gas back to a solid, that's called deposition. So we sublime something by going directly from a solid to a gas. We deposit something by going from a gas back into a solid. And so what we hope to do is sublime our product and not our impurity, and deposit our product and not our impurity. Now we need to do this under vacuum because what happens is oftentimes when you begin to heat up organic molecules, they don't turn into a gas. They just tend to decompose. And so we have to lower the ambient pressure, right? We have to pull a vacuum on it, and then we can, turn them from a solid into a gas there, right? So it's a little bit different than boiling, I would think, because boiling goes from a liquid to a gas. So we're going directly from a solid to a gas. Now, a lot of you might be familiar with this idea of sublimation. If you've ever used dry ice or solid carbon dioxide, right, solid CO2, dry ice sublimes, right? It does not turn into a liquid under ambient conditions. So if you have a block of dry ice around, it's going to go directly from a solid into a gas. So if you've ever messed with that stuff, which can be pretty cool, that is some sublimation that you guys might have seen. So let's talk about how this is set up. What you're going to need is your filter flask or your sidearm flask. You got that little Erlenmeyer looking flask, right, with a nozzle out to the side of it with a little hose barb is what we call it. So you're going to grab that. You're going to make sure it's very clean. Into the bottom of it, you're going to put your sample, and your sample is going to have some pure compound. Let's call that in blue, and you're going to have some impurities in yellow. Okay, so clean sidearm flask. Put your compound at the bottom of it. You're going to connect this to the vacuum. Okay. You're going to connect this to the vacuum. You're going to make sure it's clamped down. Right, so you got your clamp, you connect to the vacuum, put your stuff at the bottom. Then what you're going to do is you're going to have, let's do this in, let's see here, light green, sounds good. Okay, so you're going to have a setup where you have a test tube, right? You're going to have a test tube. You're going to put that into your sidearm flask, and that test tube is going to have a rubber stopper, right? So you're going to have a drilled rubber stopper. It's got a test tube that's kind of stuck through it. So you're going to put that into there, right? You're going to make sure it makes a tight seal, okay? Now, once you have that set, then you're going to open your vacuum, okay? You're not going to heat anything up yet. Just open the vacuum once you got everything sealed. You need to make sure you get all the air out of your flask, because this is where the problems happen. You need to make sure all the air is out of your flask. Now, once you have all the air out of your flask, then what you're going to do is you're going to put water and ice into here to make a cold finger, okay? Now, if you don't pull all the air out of your flask first, you're going to end up having some condensation in here, and that's going to introduce some water, which is going to cause problems. So you pull a vacuum, you make your cold finger, and this is all set up on your hot plate. And then you begin to gently warm this up. Gently warm this up, okay? Don't crank it to 10 and just, step back and watch the mayhem, okay? You're going to gently warm this up, and what's going to happen is as you heat this up under vacuum, your blue, right, hopefully your product's going to turn into a gas, right? So it's in the gas. When it hits your cold finger, it's going to go from your gas back into a solid. It's going to deposit. Then when everything's done, you're going to turn off the hot plate, right? You're going to slowly disconnect your vacuum, and then you're going to pull your cold finger out and scrape your product off the side of your cold finger, right? So scrape it onto a piece of whey paper or something like that so you can collect it, okay? So make sure you're following the proper steps. Put your sample in a clean sidearm flask, connect it to the vacuum, put in your test tube, pull a vacuum, add your ice and water, and then begin to heat it up. So just a brief conclusion, please pay attention when you're setting up the sublimation. Make sure that you're pulling a vacuum and you got everything sealed before you add the water and ice into there. Otherwise, you're going to condense some water, and then that's going to cause some issues with your purification. Don't forget you're going to be taking IR and NMR of the product. Now, your NMR is going to be a little bit, let's say, a forest of peaks. When we start to get to NMRs of cyclohexane containing rings or these bicyclic rings, you know, your axial and equatorial or your endo and your exo hydrogens are going to start being inequivalent, right? And so there's going to be some interesting splitting patterns for this. And so with the instruments that we have in the labs, what you really want to start to look for is their disappearance of your OH peak. In your starting material versus in the product that you guys make. IR is going to be a little bit more useful for us, right? Because then we're just looking at the functional groups, and we should definitely see a disappearance of our alcohol versus our appearance of our ketone. Remember, your ketones tend to pop up quite nicely, you know, between 1650 and 1750, and your alcohols are usually very noticeable out in the you know, the high 3000s to low 4000s range there with a broad peak for those. So use what you know about NMR and IR just to kind of, you know, help write your conclusions for what you need to do with respect to proving that you did or did not complete this lab.